Good morning, everyone. My name is Ilham Khefi Ramadhanu from the Faculty of Engineering and Computer Science, Universitas Nusantara, PGRI, Kediri. Today, I'm pleased to present my research entitled SmartRoad, Android-based intelligent road detection and reporting system using YOLOv12 toward sustainable urban infrastructure. This research focuses on utilizing artificial intelligence and mobile technology to improve road damage monitoring and maintenance management. Today, I'm honored to present my research entitled SmartRoad, Android-based intelligent road detection and reporting system using YOLOv12 towards sustainable urban infrastructure, submitted for Spark 2026 Student Research Competition. Let me walk you through the key aspects of the research. Road infrastructure is the backbone of economic connectivity and social mobility. However, road deterioration remains a persistent and serious challenge, particularly in developing countries like Indonesia. Based on Indonesia's 2024 National Road Condition data, 53.2% of non-toll national roads are in moderate condition, with more 1,700 kilometers categorized as lightly damaged and more than 500 kilometers as heavily damaged. These are significant numbers that demand immediate attention. The conventional approach to road monitoring relies on periodic manually inspection by field personnel. While these methods have been used for decades, they come with critical limitations. They are time-consuming, costly, and inconsistent due to subjective judgment. And most importantly, they lack real-time geospatial documentation. This means that by the time damage is officially reported, it might have already escalated into a far more severe structural failure. Thus, deficiencies collectively hinder progress toward 2K United Nations Sustainable Development Goals, that is SDGs point 9, which call for resilient and sustainable infrastructure, and SDGs 11, which promotes inclusive and sustainable urban communities. This brings us to the core question of the research. How can we develop an automated, accurate, and scalable road damage detection system that effectively bridges the gap between damage occurrence and governmental maintenance response? To address this, our research has three main objectives. First, to develop and evaluate a YOLOv12 deep learning. Second, to design and implement the SmartRoad Android. And third, to provide a GPS-based reporting system with a real-time geospatial. The dataset was constructed by aggregating road damage images from multiple heterogeneous sources, including the publicly available RTT 2022 benchmark dataset, image repositories from RoboFlow and Menelidata, and supplementary image collected through direct field documentation. The final dataset comprises 3,705 annotated images across 4 damage classes, that is, pothole, transfer crack, longitudinal crack, and helical crack. All images were annotated using the RoboFlow platform and split into a 70, 20, and 10 ratio for training, validation, and testing respectively. Now, let's look at the result. The YOLOv12 model was evaluated on the health test set using 4 standard metric: precision, recall, MMT50, and MMT50-95. Overall, the model achieved a precision of 0.916 and a recall of 0.894 and MMT50 of 0.939 and MMT50-95 of 0.711. These features demonstrate that the model reliably detects and classifies the road damage with high accuracy and minimal false positive prediction. Regarding training convergence across epoch 150 to 250, a loss component decreased stably without any signs of divergence between training and validation curves, confirming that the model is well regulated and generalizes effectively to unseen data. By the final epoch, MIP50 converged to approximately 0.94 and MIP50 95 to approximately 0.71. Let me now show you how SmartRoad works in practice. The application workflow is straightforward. The user opens the app and captures a photo of the road surface. The image is sent to the Django server via HTTP post, where the YOLOv12 perform inference and return annotated result. Detection output, including bounding boxes, class labels, and confidence scores, is displayed on the screen alongside the automatically retrieved GPS coordinate. Every detection is saved to the centralized database and accessible through two complementary interface modules. The report list displays each report in a card-based layout showing the damage, thumbnail, class, timestamp, address, and repair priority categorized as very high, high, or moderate. The geospatial map renders as each report as a color-coded mark on the digital map, where tapping a marker reveals the damage class and precise address. This dual interface design transforms SmartRoad from a simple detection tool into a comprehensive decision support system for infrastructure management authorities. To conclude, this study has successfully developed and validated SmartRoad, an Android-based intelligent road detection system powered by YOLOv12. The model achieves strong detection performance, and the application effectively operationalizes deep learning detection within a scalable citizen-driven mobile platform. By enabling anyone with a smartphone to contribute georeferenced road damage report, SmartRoad transforms the public into a distributed infrastructure monitoring network, advancing sustainable urban management in alignment with SDG 9 and SDG 11. Future direction include expanding the damage taxonomy, exploring on-device inference automation, and integrating the platform with official municipal infrastructure system. Through SmartRoad, we aim to transform every smartphone user into a contributor to safer and more sustainable road infrastructure. That's all from me. Thank you for your attention.